Everyone, my name is Jerry Kossoff, and we are here with Fiveable. It is Monday, February 3rd. It is 8 p.m. East Coast time, and we are here to do a little bit more review with our probability facts, rules, figures, and we're going to get into the specific group of probability facts called random variables. So scenarios that involve what are called random variables, and specifically a lot of time on binomial distributions tonight. Of course, you can always follow us at any of our platforms. Please be sure to do so. And what I'm going to start with is just a little bit of overview of a big picture. So if you're watching this on review, I want to take a second to talk about the big types of scenarios that get asked about, particularly in the free response section of the AP stats exam. So stats is a little bit predictable in that it's guaranteed that every year, one of the first 5 of the 6 free response questions are going to be just about probability in general. Pretty much part A, B, C, if there's a D, it'll all be about probability. And so I want to talk about some of the different scenarios that come up. And then we'll dive into these random variables. We'll start with what are called discrete random variables and then get into binomial random variables. And if folks are here, I will happy to do some Q&A at the end and help you with whatever you need help with. Hello to anyone who's joining us. So let's take a second to look big picture at the free response scenarios. Big picture wise with probability, of course, you could always get some very basic event scenarios like spin the spinner and what's the chance that it lands on this square or that square or this other square. Sometimes we'll ask to apply the law of large numbers, which is that probability represents the proportion of trials in the long run that satisfy a certain event. So the fact that a coin flip has a probability of 0.5 of landing on heads does not mean that if you flip 100 coins, you're guaranteed to get 50 heads. It means that for as many coins as you flip in the long run, they should tend to be about 50% heads. You can get asked about the probability of multiple events. So you see the two-way table in the middle of the page with athlete, non-athlete, different categories of GPA. This is a common problem stem, and then they can ask you tons of stuff with it. They can ask you for and, or, given that probabilities. They could ask you to do a scenario that would involve drawing a tree diagram, like percents of a percent. They could ask you if events are independent, if they're mutually exclusive. There are some definitions that go with that. And then tonight, we're really going to hone in on this bottom right part of your screen, where you see a table involving the number of dogs that different households have in their households. And that's called a discrete random variable. But there's also binomial random variables, geometric random variables, and then continuous random variables, which can be shown as normal distributions. All of these kinds of things are the types of scenarios that make up just about every single free response question in a probability context. Of course, they can't test you on all of that all at the same time. So it's important that you're prepared to see any of these prompts to go and get yourselves E's and P's. So at the end of this stream, I'm happy to go into any of these topics if you got lingering questions or thoughts about any of them. But for the main lecture portion tonight, we're going to talk about random variables, that list at the bottom. And we'll go ahead and start with discrete random variables. So this table at the bottom of the page represents a scenario that involves a discrete random variable. That variable X is a discrete random variable because it is quantitative. It's not categorical. So it's not high GPA, low GPA, or athlete, non-athlete anymore. Now we're talking about specific quantities of a variable X. And it's based on chance events. So in this case, we're going to randomly pick different households in a community and ask them how many dogs they have. So when I call up the household, I do not know how many dogs they're going to have. It could also be like, let me flip 10 coins and count how many of them land on heads. Discrete random variable is called discrete because it can only take certain numerical values. So here are some examples of discrete variables. Number of coins that land on heads in 10 flips can be any integer between 0 and 10. Your composite ACT score of a randomly selected student. If you've taken the ACT, you know you get a score out of 36. You can't get a 30.32. You get rounded to the nearest whole number. And so your composite score is a whole number anywhere between 0 and 36. Number of dogs owned by a randomly selected family. You can't have 1.5 dogs. Can't have 1.3 dogs. It's either 0, 1, 2, 3, 4. In this case, it goes up to 5. And we're going to ignore the few households that have more than 5 dogs. And your net gain in purchasing a single scratch-off ticket. So if you buy a ticket for $1 and you win $10, your net gain was $9. And different tickets have different prize amounts, but there's not an unlimited number of prize amounts. So scratch-off games in particular have set dollar amounts that you can win. And so you pay the cost, and then if you win a prize, you'll have a net gain. If you don't win a prize, you'll have a net loss. And so X, in that case, representing your net gain could be maybe -1 or -3 or +6 or whatever the dollar amounts might be. So the key thing here is discrete random variables involve quantitative variables, quantitative situations that are based on some kind of random event, and then you count the number of successes that you see, or number of things that you see in that situation. Might not be number of successes. Things you're asked to do with discrete random variables. Okay, you might be asked to find probabilities associated with them. Typically, they'll do stuff like the probability that a family has at least 1 dog, or 2 dogs or less, or more than this. And so the combined events in the table have to add up to 1, because they're all the different possibilities of how many dogs you could have. And since the events are mutually exclusive, you can always add things together. Like, you can't at the same time be a household that has 1 dog in your house and 3 dogs in your house. So there's no overlap between that 0.35 and the 0.09 on the table. Those are separate individuals or separate events. And so if you wanted to find the probability that a randomly selected family owns at least 2 dogs, you'd have to ask yourself, okay, what does at least mean? A common mistake that students make is they think at least means less than, when it really means the lowest it can be is 2. That's your minimum. And so at least means 2 or more. And so I would circle all the probabilities that go with 2 dogs or more. And in notation, you might see it like this. So the probability of owning at least 2 dogs in this situation, if I randomly select a family, is I take the 0.14, 0.09, 0.07, 0.04, add them together because that is 2 or more. And so I got a 34% chance of calling up a house and finding out that they have at least 2 dogs. If you are doing this in a free response setting, as trivial as it sounds, you have to show the addition that you're doing. What happens to a lot of kids is, especially with the easier, quote unquote, probability questions with these tables, it's like, oh, it's super obvious. Let me just add these together and get an answer. If you don't show your addition, you're actually not going to get the E, because the number 0.34 is nowhere on this table. So it's not clear where you're pulling it from. Anytime you're doing a calculation in a probability section, you should show that calculation on your paper, whether it's addition, multiplication, even the trivial stuff like 0 or 1, 0.31 plus 0.35 equals whatever that probability will be. So if you get a table like this, you might be asked for some kind of basic probability fact. You also might be asked to find what's called the expected value. Because random variables are quantitative, we can describe features of their distributions. Like, I could turn this table into a histogram or a bar graph, which would really be a histogram because it's quantitative, but it would look like a bar graph that shows the probabilities of each of these values of X. And if you actually did it, it would be skewed to the right. We could find mean and median. We could talk about the range. And so to find what's called the mean, its expected value, it stands for what you expect to happen over the long run. So on average, if I do a bunch of samples over and over and over and over again, what is the average amount that X will turn out to be? And this is what it looks like on the formula sheet. And it looks super scary. You'll notice there's that little sigma, that capital E looking thing is called a Greek letter sigma. What it's telling you to do to find expected value is it's a weighted average. What you're doing is taking each individual probability multiplied by each individual value, and then adding them all up. And so in practice, it's actually relatively straightforward to do. If, like, I was asked to find the expected number of dogs owned by a randomly selected family, what I would do is multiply 0 times 0.31, 1 times 0.35, 2 times 0.14, 3 times 0.09, etc. And once I get through all those, add them all up. And when I worked it out in my handy dandy calculator, it came out to be 1.38 dogs. And this is where we pause for a second and say, wait a second, you can't have 1.38 dogs. That's fine. It's an average. Even though no individual family will have 1.38 dogs, what this is saying is the average number of dogs for a large number of families sampled is 1.38. And so in very fancy AP stats interpretation, I could say, if this selection process were repeated many times, the average number of dogs owned per family would be very close to 1.38. if we could literally sample everyone, if we took a census of the whole population and asked them how many dogs they have, added them all up, divided by the number of families that we asked, it would turn out to be 1.38. But expected value is more of a like a simulation kind of thing. Like if we sampled 100 families, we would expect them to have about 138 dogs, and so it would work out to about 1.38. And so sometimes you'll get asked for probabilities. Sometimes you'll get asked for expected value. Rarely we'll get asked for standard deviation. Because this is a quantitative variable, you can describe measures of spread like standard deviation. And this is what the scary looking formula is. Although if you know the formula for standard deviation, this isn't really that far off from it. What it's saying is take each individual probability, take it away from the expected value from the mean, and then square that distance to account for the fact that some are negative and some are positive. You multiply each of those results by the probabilities associated with it. So I would do like 0 minus 1.38 squared times 0.31. Then 1 minus 1.38 squared times 0.35. Then 2 minus 1.38 squared times 0.14. Add all those multiplication results up, and then take the square root because standard deviation is the square root of variance. What it represents is the typical distance away from the expected value in the distribution. It's really not tested very much by hand, but I have seen it asked about, and so it's important that you know some like shortcuts you can do to get it. If you're watching this on replay, a thing you can do with these tables is if you come to your TI calculator and go to stat edit, you could type the list of data in. If you look at the little bottom left of the screen, you'll notice I've put in L1, I've put in all the values of X. In L2, I've put in all the probabilities. And so what I can do to get all of the statistics I would want out of this table, mean, median, standard deviation, if I go back to stat and calculate, I want to do one variable statistics, what I have to do is tell my calculator that there's what's called a frequency list. And so you tell it that I have my main data in L1 and I have my probabilities in L2. And when you come down and actually go to calculate, it will spit out for you. You see X bar is 1.38. That's our expected value. I can see the standard deviation here works out to 1.39, which would have been a lot to do by hand, but spits it right out for us. And it can even give us a 5-number summary, like the median number of dogs owned is 1, which makes sense because the probabilities in the table have to add up to 1. 1 divided by 2 is 0.5. And so I start adding probabilities until I hit 0.5, and that occurs at 1 dog. So if you need mean or standard deviation of a table like that, you can absolutely put it into your TI calculator and get it, which is kind of cool. So that is a thing. So discrete random variables, you could be asked for probabilities associated with them. You could be asked for mean or standard deviation or some kind of interpretation. And they can always combine this with some other stuff. So they could say something like, find the probability that a randomly selected family has at least 2 dogs. And then they could say, given that the family has at least 2 dogs, what is the probability that they have 5 dogs? Well, the given that, connecting back to previous lessons, means out of all the families with at least 2 dogs, so out of 0.34 is your denominator, the probability that I have 5 dogs is 0.04 out of that 0.34, and then you'd work it through. And so they can pull in some other probability facts with it, but the main typical ones are usually basic probability facts, mean, possibly standard deviation. And that's discrete random variables that show up in a table like that in all accounts. So for the next part of the lecture portion here, I'm going to go into what a binomial random variable is. This is the other main type of random variable that gets asked about quite a bit. Binomial random variables are special scenarios. And if you have this special scenario, there's a whole bunch of rules and facts and things you can do on the calculator that open up from this special scenario. And the way to make something binomial is by meeting the following conditions. And BIN is a way you can remember the things that need to be true about the situation. So the situation described to you has to be binary, meaning every trial you do either ends in success or failure. And honestly, most things can be made into a binary. Even the thing with dogs, you can, if you set the event to be the family owns at least 2 dogs, they either own at least 2 dogs or they don't. So typically stuff's going to be binary. The one that is not always typically met is that trials have to be independent. And from previous definitions, we know that independent events in statistics mean that the result of one event has no bearing on the other event, aka the probability of success for each trial must remain constant. So if there's a 30% chance of winning the first game, when I go to play the second game, I would have to still have a 30% chance of winning. Coin flips are a good example of independent events. The probability of any coin landing on heads is 0.5. Does not matter what's happened for the previous 10 flips. The 11th flip still has a 0.5 probability of landing on heads. Sampling with and without replacement is also an important distinction here. Sampling with replacement, where you take the thing out, look at it, put it back, reshake, and repeat, means that no matter what the size of your sample or population is, you're always having the same consistent probability of success because you're replacing the item every time. If you sample without replacement in a small population, you're removing individuals every time you reach in. You're changing the fractions involved for probability of success. So classic examples of like, there's 3 red marbles in a bag out of 10. Okay, well, the probability of pulling red marble the first time is 3 out of 10. But if I sample without replacement, now there's only 2 out of 9 left. And the probability 3 out of 10 versus 2 out of 9 is a very big difference in terms of decimals, 0.3 versus 0.22. So that probability didn't stay consistent. And so the result of the first trial reaching in impacts the results of the next subsequent trials, which is not the case when you have a very, very, very large population to work with. And the last thing has to be that binomial situations have to have the number of trials fixed in advance. You have to know how many coin flips you're going to do, how many names you're going to pull, how many times you're going to play this game before going into it to have a truly binomial situation. And if all 3 of those things are true, which we'll see some examples of in just a second, the only thing that probabilities are going to depend on are the parameters n and p, the number of trials you're doing and the probability of success on any trial. And once you can identify those, you can do anything that they ask you about with a binomial random variable. And then the letter x is going to represent the number of successes we get in all of those trials. So to show you some examples of situations that aren't binomial, let's look at the following. We're going to flip 10 coins and count the number that land on heads. N is 10. I'm doing 10 trials. The events are binary because every time I flip a coin, you either land on heads or tails. And the probability of landing on heads is consistent. It is independent. Every time you flip a coin, you have a 50% chance of landing on heads. So since the event is binary, independent, and the number of trials is set in advance, I can consider this a binomial situation. And x, representing the number of heads that I get, is binomial. Here's another situation that could be binomial. If I randomly select 50 students from a very large high school, and that's a key phrase there, where 45% of students are athletes, and I count the number of athletes in the sample of 50 kids, that could be a binomial situation. Every student name I pull, they either are or are not an athlete, so that's binary. The probability that I pull an athlete, if 45% of the kids in the whole school are athletes, the probability of me pulling a single athlete and any given pull is about 0.45. And since I told you I'm selecting 50 students from the start, the number of trials is set in advance. This can be considered binomial. Here are some scenarios that are not binomial. If I roll a set of dice until the sum of the dice is a 7. So like roll, 8, 9, 3, 7. Oh, I'm done. That's not binomial because it said until I roll a 7, not count the number of 7s in a certain number of trials. So even though dice rolls are independent, the result you get on the first roll has nothing to do with the result you'll get on your next roll. And you either get a 7 or you don't. It doesn't have the number of trials set in advance. This is going to be a situation that we'll see later. It's going to be called a geometric situation. And then this one would also not be binomial. If I have a group of 20 students and I'm going to select 5 names without replacement and count the number of names that belong to male students, as much as it seems like the other situation, it doesn't quite work out the same. Because I'm sampling without replacement, every name I pull decreases the total number of names left in the class and will decrease the number of males left for me to select. So let's say 10 of the kids initially were male. 10 out of 20 versus 9 out of 19 versus 8 out of 18, now the probabilities are starting to shift if you start pulling male names, or even if you don't pull male names. The probability of successfully pulling a male from trial to trial will not stay consistent. And you might be asking yourself, wait a second, the probability of successfully pulling an athlete from trial to trial may not be consistent. And technically you're right, but we have a rule called the 10% rule. So if the sample you're selecting is less than 10% of the entire available population to you, even if you're sampling without replacement, you can consider that situation independent trials. So if we imagine a 5,000 student high school where there are over 2,000 athletes, and I'm only going to pull 50 names, yes, the probability of pulling the first athlete is like 2,000 out of 5,000. And then the next one would be like 1,999 out of like 4,999. The probability is there because the fractions are so close to each other, because the numbers are so big that we're working with, are close enough that we can consider them functionally the same when we're doing binomial situations. But when we have a very small population, or we're pulling a sample that's more than 10% of the entire group, now the probabilities are going to start shifting enough when I start pulling more and more and more individuals that I can no longer consider those situations independent enough to proceed with the binomial calculations. And so that's a bit of a subtle point. But if you are not explicitly told that something is independent, if you're seeing a situation where they mention like a very large is the population, then you know that you can treat it as independent, even if they don't explicitly say that you are sampling with replacement. So once we know that something's binomial, you've got the number of trials fixed, the event's binary, and the probability of success remains consistent from trial to trial. The only thing that the probability depends on is how many trials you did, the probability of success, and how many successes you wish to see. And there is, hey Jess, welcome. There is a formula on the formula sheet that looks horrifying to some people. And this is what it looks like. This is how to calculate any value of x for a binomial random variable's probability. So the probability that x equals 3 is all of this stuff. And that thing in parentheses is called a binomial coefficient, which is like the number of combinations that you can have. So I'm trying to think. Right now, our 10th graders in my school who are in the like advanced honors track are doing binomial expansion, where they have to do like a plus b to the 8th and expand it out to be like a to the 8th plus 8a to the 7th b plus, I don't know, it's 20 something a to the 6th b squared, and it's this giant polynomial. Those coefficients that show up as part of that expansion is that number there. And if you ever need a binomial coefficient, the way to get it on your calculator is to use, it's called combinations. It's a little NCR thing. I think it's number 3. If you go to the math button, slide over to probability. So for a clear scenario, when taking blind guesses on a multiple choice questions, your probability of getting an answer correct is 0.20. No idea, just put B. Who knows? I got a 1 out of 5 chance of getting it right. If I blindly guess at 6 questions, what is the probability of getting exactly 2 correct? The reason that I'm not just going to do 0.20 squared times 0.8 to the 4th, which would make sense of like 2 correct answers, 2 successful results, times 4 unsuccessful results, which would be 0.80, 1 minus 0.20, is that I don't know which questions I'm going to get right and which questions I'm going to get wrong. There are multiple ways for that to happen. Like I could get numbers 1 and 2 right and the rest wrong, or I could get numbers 1 and 3 right and the rest wrong, or numbers 1 and 4 right and the rest wrong, or numbers 1 and 5 right. And you can see where this is going, that there's going to be a lot of different combinations that work themselves out that lead to 2 correct answers and 4 incorrect answers. And that makes a difference because me getting 1 and 2 right and the rest wrong is different than someone else getting the first 4 wrong and numbers 5 and 6 correct. Even though we both got 2 out of 6 right, we got different questions right and wrong. And so those are 2 different outcomes. Those count differently. And what the binomial coefficient takes into account is how many of those combinations there are. So in this case, I would need to find what 6 choose 2 is before I could multiply it by these appropriate probabilities. And so I'm hoping that you can see from this situation how the formula might look. But then I'm going to show you another way to get it on your calculator. So take a look at this. Notice P is the probability of success. X is the number of questions I want to get. So that's where the 0.20 to the second power is. 0.80 to the fourth power shows up because that's the number of failures that will happen in this situation. And then that coefficient in front, that 6 choose 2. If I go to my calculator, NCR, I'll put the 6 first and the 2 second, and it says 15. What's the big X? Yep, the big X stands for the general like random variable. So X will stand for what the situation's about. So in this case, number of questions answered correctly is the big X. So this statement says the probability that the number of questions I get right is 2 is going to be equal to whatever the coefficient from 6 choose 2 is times 0.2 squared times 0.8 to the fourth. And since that coefficient is 15, I'll do 15 times 0.2 squared times 0.4 to the eighth. And I'm getting a very, very, very small, oh, I said eighth. I just switched 0.4. I just typed it in wrong in my calculator. I did 0.4 to the eighth instead of 0.8 to the fourth. And I am getting not the right answer because I just put the wrong thing in and now my batteries are dying and oh my goodness, this is a mess. Well, I'm going to show you how to do it again in a second. Good. Just asking, before doing it, do we have to show that we tested the conditions like the 10%? Actually, no. Typically, this is not something where it's like hypothesis testing or confidence intervals where you need to set everything up first. You just, yeah, actually, I'm going to actually double check a couple of rubrics. I don't think so, because 10% is usually not one that is explicitly asked for. And if they're giving you a situation that could be done binomially with the like random selection, it will have come from a very large population and your sample will be very reasonably less than 10% of that situation. So I don't think any rubrics explicitly ask you to do it. Your teacher might, but AP exam shouldn't do so. Let's see if my calculator's working again. So we're back. 15. I'm actually going to get the answer here and then show us another place to get it. Times 0.8 to the fourth. Oh, there we go. 0.2456. That sounds about right. There's another place to get this. And if you haven't seen this yet, be ready to be wowed because it's super great. There's a button called BinomialPDF, which is a way for our calculator to do everything for us once we know what the parameters in the situation are. So the way to get there is you go to the distributions. If you did normal distributions on your calculator, it's the same menu. So it's second and vars, the button right underneath the arrows. And you're gonna have to scroll down a ways to choice number A. I put 0 on there, that's a typo. It is choice number A or letter A. And once you do that, you're gonna get a little menu that'll have trials, P, and X value. If you have a newer calculator, it should have this interface as well. We have 84s at my school. I know that's still a very popular calculator. If you have a TI-83, ask me later because you're gonna have to type a lot more stuff in. If you have an Inspire, I think it should be a similar menu to this. And if you have another brand, I don't quite know how to help you. I hope there's another way to do it. In the situation we were just looking at with the 6 multiple choice questions, I put a 6 for trials, I put 0.2 for probability, and I put 2 for the number of X that I want. And it should work out to the exact same thing that I got earlier when I did all of the crazy coefficient stuff with 15 and 0.2 and all the squared and all that lovely stuff. And so it will work if you want exact probabilities in this situation. I have another way to do it though, if you're given situations that are not exact. And so this is probably, if you've done it in class, or I know Richie, I think you might be self-studying, you might have seen some samples in your book. I have another way to do it. So let's look at a situation. And I'm going to come back to this in a second. The moral of the story is we're going to use summation notation to kind of cheat for us a little bit. And instead of typing a specific number in for X, we're going to leave the variable X there for it. And then we're going to type the boundaries in the summation and let it add up all those things for us. So let's look at a specific situation to get a sense of what I mean by this. So while shipping a large quantity of electrical components, some will inevitably break. Data show that for a computer parts supplier, 3% of their computer's components will break on any given shipment. Assumed shipments and whether or not a component breaks are independent events. They tell us it's independent. What is the probability that in a shipment of 50 components, at least 5 are defective? 50 components means 50 trials. They said it's independent. 3% means 0.03 for the probability. At least 5 means X has to be 5 or more. So in this case, I could find the probability of 5, of 6, of 7, of 8, of 9, and just keep going all the way to 50, but that would take a lot by hand. There's a button that's called Binomial CDF, which accumulates the results, but it only accumulates up to a certain point. It won't do a set interval for you. So this little hack is a way that you can do it all at once for yourself. And so this is what I want to be typing into my calculator. The way I get there is the summation is, at least on 84s, it's on the shortcut menu where the window is, alpha window, and you can get a big summation. I would set up all the stuff I want first. So I want from 5 to 50, and then scroll over to the center, and then I'm going to go to the binomial PDF page. So second distribution, letter choice A. I have 50 trials. My probability is 0.03. And I'm just going to have the hack here is just have X be X, because then your calculator with this notation is going to know you want me to calculate the binomial probability of all of those things from 5 to 50 and add them all up for you all at once. And it's going to take a second to think about it. And unfortunately, my batteries are low and it just died. But I can see 0.0168 came out of that because it knew to do 5, 6, 7, 8, 9, 10 and add them all together all at once. And if you write this exactly the way it's written right here, the only other thing you would have to do to get credit for a free response answer is label 50 as N and 0.03 as P, which you should be doing in the first place. As soon as you're doing a binomial, you recognize a situation as binomial, you should identify binomial, N equals P equals, and then do whatever calculation you're going to do, because just identifying the situation as binomial usually gives you a partial credit. But if you don't identify what N and P are, that's also not enough to get full credit when you actually do the calculation correct. And so that's my little life hack for at least 5 or up to 10 or things like that, is leave X as X, use a summation notation, and put your boundaries on the edge there. Anyone in here? Well, let me do one more like lecture-y thing, and then we'll do some questions and chat with those folks that are here. Another type of random variable that you could see is geometric. Very, very similar to binomial. Okay. The only difference is the number of trials are not set in advance. And instead, what we're doing is seeing how many trials it takes until we get a success. So we're going to know P. We're going to know that the situation's binary. We're going to know that it's independent. But what they'll do is be like, how many flips does it take until you get, how many games must you play until you get this thing? And so the probabilities there are really specific events. You have, if they say, what is the probability that it takes you 7 attempts to do something? That means the first 6 attempts were all failures and the 7th was the success. And so you're going to end up with that being the formula that's on the formula sheet. But break it down, all it's saying is, I made a mistake on that. That should be X minus 1 is the exponent. I'm actually going to go change this like literally right now. I can't. Just kidding, because it is a image that I put there. So I do apologize. That should be an X minus 1 at the top. And then P is the last one. Because if you're doing 7 trials, that means you have 6 failures and then a single success. That's what it looks like on the formula sheet. Other things you could be asked with binomial and geometric random variables involve mean and deviation, just like before, expected value. Straightforward calculations. If you have a binomial random variable, your mean is N times P. So for example, in the athlete scenario, if I'm going to pick 50 athletes and I know that 45% of the school are athletes, I multiply 50 times 0.45 to see how many athletes I expect to get in my sample. Take whatever the total number of trials is, multiply by the probability of success. That's what you should expect. If you think about it, like if I do 10 coin flips, I expect 5 of them to be heads because 10 times 0.5 is 5. If you're doing a geometric situation, the length of time it takes to get the first success should be expected to be 1 divided by the probability. So if you've got a 50-50 chance of something happening, you expect it to take 2 trials until you get a success. That would be the average it would take. If you got a 10% chance of something happening, the average it would take would be 1 over 0.10 or 10 tries to do something. You, of course, might finish sooner. You, of course, might finish later, but that's just what we expect to happen. Standard deviation for binomial random variables doesn't get asked about a lot, but you take the number of trials times the probability of success, multiply it by the probability of failure, and put it all under a square root. You're going to see this standard deviation formula show up in a lot of different ways once you get to inference and sampling distributions. And like you'll see this N, some people call it Q for the probability of failure, NPQ. On the formula sheet, it's NP1 minus P. I have not seen this asked about much by itself. So it's just kind of there as a thing. So just like with discrete random variables, you could be asked to do probabilities. You could be asked to do mean and deviation, and you could be asked to interpret stuff or combine it with previous events. So once you know the probability of getting exactly this, or at least that, given that that happens, what's the probability of this other thing? Or if it doesn't happen on the 10th attempt, the probability happens on the 11th, or other kinds of combos. And as we get closer to exam time, we'll really start looking at specific problem sets that go with things. So as a recap, and Jess, hopefully you're still here, these are all the things that come up in free response scenarios. I analyzed the last like 6 years worth of free response questions. And so last year, the probability free response question started with a 2-way table. And part A was and or given, all 3 of those. Part B asked if 2 of the events on the table were independent. And part C said, what is the probability that at least 4 of the 5 do whatever the thing was? And it was a binomial situation because it was 5 trials from a large population, and the probability was consistent because they were separate people or whatever it was. 2 years ago, the situation started with this % of people do this other % do that, and it lended itself to a tree diagram. So you built the tree diagram. Then there was a given that this thing that in part A you calculated happens. What is the probability of this other thing? So you use the given that probability. And then part C was another binomial situation, is if you pick 10 people from this giant population, what's the probability that at least 2 of them do the thing that you calculated? Normal distributions also show up pretty commonly. That was one 3 years ago. The probability scenario started with a normal distribution. You found a probability that went with it. And then the next parts were a conditional and a binomial situation that built off of that. So those are the common things that happen. I think this year, if I'm a betting man, which I am not, let's be clear, AP stats exam makers can do whatever they want, and they're not always consistent. I think we're due for a situation that starts with one of the tables like in the bottom right, where it's a discrete random variable. And then we might get asked some basic probability facts, maybe expected value, and then some kind of extension connecting it to something else. Perhaps like you calculate a probability and make it a p-value that you compare to something. We'll see. To give a little preview of what's coming up at Fiveable here in the next couple of weeks, I'm going to stick around for a little while if we want to do some open questions because we got some time, but my lecture part is definitely done. I'm going to get into reviewing sampling distributions. So once you usually finish the probability unit, you start moving into inference, and the foundation of inference, in addition to probability, is understanding how sampling works and how sampling distributions come to be. So we're going to focus on everything to do with proportions, sample proportions, next Monday at this time. And then 2 weeks from now, the 17th, we'll do everything involving means. So we will include 1 samples and 2 samples and discuss all of those formulas on the inference table, on the formula sheet on the AP exam. Where do all those come from? What do they all mean? What do they tell us? What happens when the samples get bigger? What happens when the samples get smaller? What all the notation's about? And we'll be looking at those in the next couple of weeks. But I wanted to take any open questions at this point. I know some folks have been watching. I know I've done a lot of talking. I know you haven't necessarily done a lot of typing. But if you want to do some more practice problems, if there's a specific topic you want me to, I can make some problems up. We can just do them. Or if you have any other lingering questions, you can type them in the chat. If you want to say, Thanks, appreciate it. I'm all good. That's cool too. But I'm gonna let you guys type for a little bit, and if I don't see anything in a couple of minutes, I will wrap up and say goodbye. So thanks for watching. If you're on replay, the lecture is done now. It's going to be some open questions for the folks that are live. Cool. Practice problems will be helpful. Jess, do you have a specific, do you specifically want practice problems with binomial random variables? Do you specifically want me to do some stuff with that discrete table at the bottom? Do you want to do some stuff with the two-way table in the middle? I could just kind of bounce around, but if you have one that you really want to look at, we can do that. Any of them. All right. All right, Jess, let's start with this. All right, so I just typed one in the chat. Given that a student at the school has a low GPA, less than 2.5, what is the probability that they are an athlete? So that would be using the two-way table. And that would be the conditional probabilities. The phrase given that is a really key phrase. You can type an answer as a fraction, or you can type, I'm not sure. Let's see. All right, Richie says 40 out of 95. Okay. I'll wait about 20 more seconds to see if Jess gives an answer before I give feedback on it. I think I agree. All right, Jess, I think you are right for agreeing. The key phrase was given that. Given that is always code for what your denominator is going to be. And so in this case, given that they have a low GPA, that means out of 95, probability that they're an athlete, there's 40 athletes in that category. And so that's an application of the formula right above that table, where B is low GPA and A is athlete. So all the athletes with low GPAs out of all the people with low GPAs. Very, very good. Let's do another one. You just calculated the probability of being an athlete given that you have a low GPA. So 40 out of 95 is 0.42. Based on that, does it appear that the events of being an athlete and having a low GPA are independent of each other, or do they appear to be associated with each other? So does knowing that someone has a low GPA, does that impact the probability that they are an athlete? And so what we need to compare is versus. We need to compare those things, would be how we determine if something is independent on a two-way table. All right, we got a yes and we got a not independent. You can elaborate a little bit, or if you're willing to elaborate a little bit. So independence has to do with, is the conditional probability the same as just the overall probability? So 40 out of 95, I got 0.42. The probability of picking an athlete in general, yeah, is 190 out of 500, which is 0.38. Close, but since it's not the same, it is not independent. The situation on last year's AP exam was actually independent. The probability in the column was the exact same as the overall probability of what the situation was. Let's do one with the table at the bottom. That table shows the distribution or the relative frequency of the number of dogs that people in a large city own. You are going to take a randomly selected sample of 10 households. So randomly select 10 households. And you are interested in whether or not those households have at least 3 dogs. So interested in at least 3 dogs. So before we get into anything with that, let's just start with what is the probability that any of the selected households has at least 3 dogs? .20. Yep, just add together the 3, 4, and 5 probabilities. Okay, in my sample, and Jess, I know that this isn't the actual AP exam. You would get P, Richie would get E because Richie's showing his addition. And so anytime you're doing a calculation that isn't directly on the table, you need to show what it is to get the full credit in a free response situation. I don't know if you were here for that discussion at the beginning, though. Okay, so now with that, if I randomly select 10 households, let's calculate the probability that, do we have to show like a formula? No, just that you added. So this, pretend this 2 is a greater than sign, or sorry, pretend there's an equals on this greater than sign because I don't know how to type it here. Like this is what the official rubric would have said with the equals. Oh, wait, no, sorry, I should have meant that 3. So I guess technically that's not right because it is greater than 2, but it would be P x greater than equal to 3 equals plus 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 equals 0.20. But having that probability notation is not required. It's just showing the addition that's required. Okay, what was I going to go? All right, we're going to randomly select 10 households. What is the probability that exactly 3 of the 10 households have at least 3 dogs? You can either give me an answer or explain what you would either write out as a formula or type into your calculator to get it. Oh, just wait. I guess I have to delete my stuff to see what the 0.201. All right, let's find out because I just made this up, so I don't know what the answer is. What did I say? 10. Okay, 0.2 and 3. Jess, this is me giving you some shine. So however if you were in a free response situation, you would need to clearly label what you did to get that number, even if it's something you typed in your calculator. And just copy pasting what's on the calculator screen is not enough. You'd have to label n equals this, p equals this. And so in this case, I know because it was described as sampling from a large population, this people are independent. And we already figured out p was 0.02, n is 10. x is 3. This is a binomial random variable. And then I can use, then once you label those things, you can then say, you can actually type out 10, 0.203, and then give that probability that you did, rounded to the nearest thousandth place. Just the second thing I typed in by itself without arrows pointing to 10 and 0.2 as n and p will get partial. But if I label them as n equals 10, p equals 0.2, this is a binomial situation, then I can type it, get the full credit for that. I'm trying to think if I have any other. So I don't have any like single tables go, but I would probably do an expected value situation with a discrete random variable. That would be good, but I think that's some good. Any you wouldn't have done the top. Okay, yeah. It's so frustrating with the probability questions being someone who's grading like real rubrics, because it's so clear that like there are tons of kids who know what they're doing, and because they're not labeling all the setup, kind of like when you have to check the conditions, you have to just like you have to show every single piece of every single thing to get the E. So there's people who are like clearly doing the math right who get partials, and like partials start chipping away at the scores and it starts to add up. And then if you happen to accidentally make an error in that too, now you go from getting it fully right to now getting a totally incorrect I. But you clearly knew what you were doing, that it was a binomial situation. It's because calculator speak doesn't count. So like with normal distributions, you can do normal CDF in your calculator, but if you don't sketch, shade, label, and shade the curve on your paper and then say normal CDF equals whatever the answer is, you're not going to get the full credit unless you show clearly what that is. So definitely err on the side of showing more calculations or more labels than you would. My question is about the 503, the X one. Okay, so that was back when I was talking about doing some situations where we want to add up more stuff. So the same thing with now, instead of the probability that the household has, or that 3 households have at least 3 dogs, let's do the probability that at least 3 households have at least 3 dogs out of the 10. So same situation, n is 10, p is 0.20, it's binomial, and now we want x to be greater than equal to 3. One way you can do this is, of course, do binomial PDF for 3, 4, 5, 6, 7, 8, 9, 10, and then add them all up and almost like make yourself a little table. But that would be really, really time consuming. You could also find the probability of 0, 1, or 2, add those up, and take it away from 1 to get the leftover stuff. But Richie, to answer your question, what I'm going to do for my little hack that I like to do is I'm going to open up a summation, which comes from second window or alpha window on mine. It's choice number 2, and it's going to pop up just like a summation notation, kind of like this. And so I can actually type in, if I want x to be at least 3, that means x can be anything from 3 to 10. So I say x equals 3 at the bottom, 10 at the top. The lower boundary is where I start, and the upper boundary is where I want it to stop. And then I come over here, and while my cursor is like printed in the screen there, now I'm going to go to second vars and do my binomial PDF stuff. And so the same thing, I had 10 trials, probability was 0.2, but now I don't want just x equals 3. I want x equals 3, 4, 5, 6, 7, 8, 9, 10. And so I'm going to cheat by putting x there, because now my calculator is going to know, oh, that 3 to 10 that you put on the summation, I'm going to plug all those numbers in for x, run binomial PDF for them, get all the probabilities, and add them all up for you at the same time. And it's going to take a second to think about it, but it doesn't take too long. So the probability that at least 3 households have at least 3 dogs is 0.3222 in this case. Realizing it's backwards on my screen. I hope when it's streaming to you, you can actually see it forwards. Not really sure. Okay, cool. That clarified it. Awesome.